Okay, so in this video, we're going to look at an application of linearization. In particular, we're going to look at using L'Hopital's rule, which you will recall is a way of evaluating limits. Now, understand that we have certain conditions in order to be able to use L'Hopital. So we're looking at a situation where we have the limit as x approaches some value, that could be any real number or infinity itself, of a function divided by another function. And if this turns out to be of the form either 0 over 0 or plus minus infinity over plus minus infinity, then we can use L'Hopital's rule on it. Now, there are some restrictions on f and g. They both need to be differentiable in a neighborhood around a. So f and g differentiable near x equals a, but not necessarily at x equals a. So that gets a little tricky. But for the examples we're going to be looking at, we'll be safe on that. So this first example that we're going to look at is this one here. The limit as x approaches 0 of 1 minus e to the negative x over sine of x. So the first thing that we want to do before we even get into L'Hopital's, let's take a look at the graph of, first off, we're going to take a look at the graph of this entire function here. Okay, and it looks like this. And from this graph, we would anticipate that the limit is 1. So notice as we approach 0 from the left, and as we approach 0 from the right, they both appear to be approaching the value of 1, even though at 0, the function is undefined. Now, if we think about what L'Hopital says, L'Hopital basically says that the limit, so let me do this in black here, the limit as x approaches a of f of x over g of x will equal the limit as x approaches a of f prime of x over g prime of x. Now, think about what that's saying. That's saying that what we're concerned with, and again, note, for L'Hopital's to apply, one of these two situations has to occur. So let's just, for the sake of argument, assume that we had a situation where we had 0 over 0. That means f is going towards 0 and g is going towards 0. So then the question becomes that we answer with this is how fast do they go towards 0? Okay? Because that's in essence what the derivative is telling us, the rate at which f is going towards 0. We know f is going towards 0. Now we're asking how fast. And we're also asking that about g. And so in a sense, what this is telling us is the rate, it's really telling us the ratio of the rates. And if f is going faster or if g is going faster, then that will dictate what the final answer is. So if we look at these individually, so notice here, if I look at this function, consider it to be f, and this function, consider it to be g, if I look at them individually, then I wind up with this. So this one right here is the sine of x. Notice it does go towards 0. And this one right here is the 1 minus e to the negative x, and it also goes towards 0. And so the question that L'Hopital is really going to answer for us is, how do they go towards 0? How fast do they go towards 0? Well, if we examine this, it appears that they're heading towards 0. If you look at this kind of the rate here, it appears that they are going towards zero in a one-to-one fashion. In other words, they're going towards zero at the same rate, right? Because the slope here appears to be the same for both of them. And that's why it makes sense that the limit is going to be 1, because if this is going towards zero at a rate that is nearly the same as what this one is going towards zero, then as you get closer and closer to zero, the limit of the function values should be 1. All right, so how do we apply L'Hopital's? So to apply L'Hopital's, what we do is we have the limit as x approaches 0 of 1 minus e to the negative x over sine of x. Now, keep in mind, we're going to, in order just to inform the reader what you're doing, we're going to put a little h here to say, hey, I'm using L'Hopital's, and we take the derivative. Now, be careful. We're not using the quotient rule. We're taking the derivative of the top, which would be e to the minus x. Note you have to, the derivative of 1 is 0, and you have to take a chain rule here because of this, and so that makes it a positive, over, and the derivative of sine of x is cosine of x. Now, as x approaches 0, this is going to be 1 over 1, which is 1. So from this, we can conclude that the limit of our original quotient is 1. And that agrees with this evidence of the function and this evidence of each individual function heading towards 0 at about the same rate.